Hello, my session today is on the basics of radio waves and software-defined radio. The topics that we'll see are the basics of radio frequency communication, the radio spectrum, the range of frequencies involved, and the different types of licensing in those. Examples of a common radio architecture, so you get more of a functioning of where SDRs tie in. And finally, software-defined radios, the concept, products, software systems, and their uses. Not covered in this, but topics of interest, if you expect to go further, are all the following at the bottom. For those, there's many reference books, or there's the work amateur radio classes, which are good places to further radio knowledge. The basics of radio waves are if you take an alternating current signal in a wire, bring it to an antenna tuned to to that frequency, it will transmit radio waves. And similarly, if you take the radio waves, bring them back, and an antenna receives them, it will output an AC signal, which can be brought back to electronics and used. There's a lot of other details in the process. For example, at what frequency the signal operates, what is the transmit power of the transmitter, the sensitivity of the receiver, what is the bandwidth of the signal, types of modulation. A lot of radios can go to faster speeds, but that requires more signal for them to operate correctly. Is there line of sight between the antennas? Can you see one antenna from the other? Oh, and also, is the Fresnel zone open? That is one of the factors in radio path planning. Trees, buildings, land, elevation can all block signals between two antennas and reduce it. And lastly, the pattern of the antenna itself, if there's any interference in the area. And there's also some time-dependent effects, such as fade, multipath, and other such issues. And all of these fall into affect how well radio communications work, what areas are covered, how far a signal will go. For antennas, we'll quickly touch on that for one slide. Antennas are mainly classed by gain. If you have a water hose, for example, the more it focuses the water, the more pressure you get. Similarly, for radio signals, there's a huge difference in the range that you can get, depending how willing you are to focus the coverage. The lowest gain antennas are the type you see on routers. Fully omnidirectional antennas. They send the signal equally in all directions. And when you have a router in your house, this does mean you're wasting signal broadcasting straight into the ground or straight up into the sky. If you want a bit more coverage in your house, then you can get a donut type omnidirectional antenna. That most of those are around 10 dBi of gain versus the near 0 dBi of a fully omnidirectional antenna. These have a donut coverage pattern where it covers more to the side where usually people are, and it spends less power transmitting into the ground or straight up into the sky. Even higher gain than that, you start getting in the area such as sector antennas. When you look at cellular towers, you'll notice quite a few panels up there. Most cellular towers have 360-degree coverage, and they achieve that by having three sectors of 120 degrees. Each of those angles has anywhere from 1 to 4 antennas serving customers in that 120-degree angle of the tower. Most of those antennas are about 15 dB gain. Even higher gain than that, if you have a neighbor down the street and you want to steal their Wi-Fi, you can get a high-gain grid antenna. Those are often seen for longer distance Wi-Fi networking, and those have 24 or 25 dBi gain. those focus the signal to about 15 degrees wide. So they do start to need to be aimed pretty precisely at the location you want to either send or receive a signal, so that you can get the signal you want where you want it. Even higher gain than that, that we get out of the consumer area, and you get into the backhaul dishes. If you look at cellular antennas, there's the big, often white covered dishes. If you're wondering, that little lightning is the Andrews or CommScope, I believe, logo. Those have extremely high gain, 30, sometimes 40 dB. And those often have a beam width of about 2 degrees. So if it wasn't for the fact that these were attached to the tower with 100 pounds of solid metal, if you just pushed the antenna a bit, they would lose all their signal. And those are often working at higher frequencies, 6, 11, 18 gigahertz, and are used only to connect cell towers or other towers to each other. The radio spectrum is mainly organized by frequencies. Here's the table of the Canadian frequency allocations. The way frequency allocations work in the world is that there is the International Telecommunication Union that creates kind of a template for radio frequency usage. After that, world governments take that template and modify it for their own reasons and purposes. And all of this determines who can use what frequencies for what purposes. For your information, we mostly will talk about frequencies, but there is another word for that called wavelength. The terms are inversely proportional. Higher wavelength means lower frequency. In the radio spectrum, it is extremely wide. So the first thing we'll start with is by telling you you can ignore 99% of it, just to keep things simpler. The spectrum is from 1 hertz to 3,000 gigahertz. Of these, you can ignore pretty much anything under 30 megahertz, because those have antennas that are literally the size of your house. If you have a neighbor in your block who's an amateur radio operator, sometimes some of those guys use, for example, the 80-meter band. 80 meter is actually the wavelength. The radio waves are 80 meters long. So that means if they put up one of the shortest antennas they can put up, a quarter wave antenna, it will be 20 meters long or 65 feet. Sometimes when you see ham radio antennas and they have a line going diagonally from the antenna to their house, often that's not a guy wire to stabilize the tower. That is the actual antenna. So out of those very specific uses, no one uses, or very few use, under 30 megahertz. Similarly, above 30 gigahertz frequencies, the wavelength is so small that anything affects the signals. Even rain will start heavily fading those signals. As such, they're extremely line of sight. They won't go through walls, they may not go through paper. So though above 30 gigahertz, the only users are some satellite cases and short distance, very high capacity backhauls. So dishes that go about 1 or 2 miles and can do 1 gigabit or 3 gigabit. Often it's companies who are just connecting one building to another and want to send 3 gigabits of data like a few hundred feet. Ciclu, Bridgewave, those types of companies who sell links for 20 grand a link. In above 6 gigahertz, there is a good bit of usage, but we won't be looking at it much since the only big users are satellite connections, TV, for example, some satellite internet, and some of those backhaul dishes between the cell towers or other towers, which are really directional. So the most human activity that happens in the radio spectrum, and the most interesting place to either receive or transmit, is about 100 megahertz to 6 gigahertz, very roughly. And in this range, what I call the beachfront property is 200 to 1,000 megahertz. That is the preferred spectrum because it's high enough that you don't need antennas of the size of your house, but it's also low enough in frequency that it can go through walls, buildings, trees fairly well. Once you start getting into the 2, 3, 4 gigahertz range, you start getting, because those are higher frequencies, shorter wavelengths, then you start seeing the effects of all those obstructions quite a bit more. So of this radio spectrum, as you saw from the Industry Canada chart, there's a lot of colors, a lot of users. Of those users, most fall into the license category. That means mostly companies or organizations that are paying the government to use those frequencies. License users, most people know the broadcast license users. For example, FM stations, 106.1 and the like. Those have pretty thin signals. They're just 75 kilohertz wide, which is 0.07 megahertz. And their signals are spaced at 0.1 megahertz from each other, usually in the range of 87.5 to 108 megahertz. Many people also, another popular use is TV signals. Because there's a lot more data, because the video, those signals are a lot wider. They're 6 megahertz wide. And they are spaced in various, very haphazardly, randomly, between 47 to 854 megahertz. It's actually a very large range, and it's because in the history of telecommunications, they kept adding TV channels at certain spots as people asked for more TV. So these TV channels are interspaced between a ton of other users. And it becomes difficult to actually manufacture TV antennas because they are so wideband. Two-ways or walkie-talkies are another popular use. Those are very little, they use very little bandwidth, just say 25 kilohertz wide. And often those are licensed around frequencies of 150 to or 450 megahertz. They tend, for a few reasons, usually the ease of manufacturing hardware, they're often fall into those ranges. There are terrestrial point-to-point links. When you have a TV station, they create all the video, the content at the studio, and then they just send it to a transmitter in Eli, Starbuck, or on top of the Radisson, etc. And often those use a studio to transmitter link. And a number of those are around 940 megahertz. And cellular is a big usage that everyone's knowledgeable with. Those channel sizes are extremely variable as cellular providers are always optimizing and changing their network and coming up with new protocols. They seem to be more around 6 megahertz channels, but there's a huge number of sub-channels depending on the various protocols involved. And those are around the 850, 1700, or 1900 megahertz. All these licensed users are allowed very high transmit power, and so they can reach pretty far distances depending on how high their towers are or sites are. How much money they spend on these licenses is very variable depending on how wide their channels are and for how big of an area they licensed it. For example, there's some rural farms who put a radio repeater on their grain light just to cover the farm area. And walkie-talkies use a very small channel, say 25 kilohertz. So if they get a license for, say, 160.025 megahertz for a large rural area, they may just pay $100 a year. Whereas the much in demand 700 megahertz spectrum, that was used previously by TV broadcasts, but with the heavy reduction in use of off-the-air television, most of those broadcasts have been shut down. That spectrum has been auctioned, and since it is in the middle of the beachfront property, as it's worth a lot of money. The Government of Canada carved out 108 megahertz of spectrum around 700 megahertz. They divided in multiple blocks, and each of these blocks covered certain areas of the country depending on population density, geographical distance, and the like. And they sold them for a total of $5.3 billion to 97 companies, which is pretty nice for what were just unused TV frequencies. So these licensed users are the primary users. As we'll see later, there's other secondary classes of users. All these frequencies are entered in the Industry Canada Spectrum Management System, a huge and extremely important database that includes all the sites, what areas they cover, what frequencies they cover, and that is used when doing all the planning to make sure that the primary purpose of the license system is that when you pay for a license, you're guaranteed no one is interfering with you. That database is accessible at smssgs.ic.gc.ca. You can do searches in there by geographic location, frequency range, or owner, and result in either annoying to use HTML or CSV file, which can be processed later. One popular example of this is the ertyu.org Canadian cell towers map. That site scrapes the database and puts it in a Google map. So you can see all these cellular towers, what frequencies they use, and who is the actual owners of them. So if you have a cottage in the middle of nowhere and you are installing a cell booster to get more cellular service, you can look at this near your cottage and see in which direction to install the antenna on your roof or on the tower for your cell booster. Now, I'm actually doing some radio licensing for new 18 gigahertz links for my employer. So I thought I'd give you an example of how this more advanced planning works. When you are applying for an Industry Canada license, it's quite a long process because it's engineering. That's what it comes down to. So first of all, you need to plan your radio path using multiple variables. In this case, we'll say that we're doing a radio link between two different towers in a rural area. Factors that are included in the planning are the height of the structures, what's their wind load, which means how big of the dishes you can put, how you can mount equipment, what frequency you use, the models of the radio and the antennas, the estimated signal over the radio path, the speed in megabits you can get, the percentage of availability of those speeds based on other factors such as fade and interference. That's more for unlicensed links, that is for unlicensed links, not licensed links. Any obstructions such as trees, and factors such as keeping it upgradable later. Here is an example of a path I've been planning between two sites 10 miles away on 18 gigahertz band. So in the middle top, it says RX level -45, a very nice signal. And the software does planning based on land elevation, any trees in the way, some other factors to estimate to give a quite accurate estimate of the signal level that we'll get. And it can be tried with different heights, different antennas, different frequencies to see the most optimal signal level and, of course, the least expensive option. This is different software that actually includes the speed in megabits. So you can design certain, we put in the antennas, the GPS locations, it calculates the signal level, and in cases of unlicensed systems where there can be interference, what speed you'll get depending on that interference. Or for licensed systems, mostly it's a question of availability. In cases of occasional fade, how can you guarantee it? Or you'll get like 230 megabits at least 99% of the time. So it's there's lots of different options that can be tried to get the most optimum link. The radio system licensing process is not just planning your path, it's planning all the others. And that gets quite long. After you calculate your path, you use the Industry Canada SMS to get the list of all other users in that area who are using those similar frequencies. And then you need to map all those other users and calculate the signal from their antennas, their locations, using their type of antennas they use to you. And then you need to prove that you will not interfere with their systems by showing what signal what level they'll receive your signals at, what levels you'll receive their signals at. All of this needs to be then reviewed, stamped by a professional engineer, sent to Industry Canada, who they review it, and then the other licensed users in the area will also review it. They'll complain, sometimes for extremely stupid reasons, and like you wouldn't believe. And then you wait a long time, and after this whole process is done, you can get a radio license so that you're guaranteed your own frequency that no one will interfere with, or hopefully. Or I should say, or more, you can complain to Industry Canada if someone interferes with you, and they will give them a $10,000 fine. So either way, you get results. Here's an example of licensing I'm doing. These are all the 18 gigahertz sites near Winnipeg. So these are places with those larger dish antennas, anywhere from 1 foot to, I think, 6 foot wide antennas. The vast majority are cellular sites, Rogers and Telus. MTS owns the phone line, so they don't need to do many radio links. And there's also a few commercial users, mostly wireless internet service providers, some school divisions who have rural schools, and some other commercial organizations who have a bunch of far out sites and who set up their 18 gigahertz link to get them links to get them well connected. This is the 18 gigahertz users in Winnipeg, which I plotted out for my licensing, and it shows you all the path between them. Most of these, again, are cellular sites, and these 18 gigahertz links carry the traffic that then goes to the cellular antennas and actually feeds the users. So that's it for the licensed users of the radio spectrum, or I should say the real licensed users. The next priority of users after that is amateur radio. So that is, amateur radio is somewhere between a hobby and a community and an emergency response service. There's a series of frequencies set away for amateur radio use. There's many under 30 megahertz, those being the 80-meter ones that require the huge antennas. And there's multiple other kind of spots that have been set away around 144, 440 megahertz, 900 megahertz. In some cases, amateur radio users are secondary users, which means that they need to check that no one else is using that frequency in that area before they start using it for their own fun. In some cases, the frequencies are strictly amateur radio, so they can do anything they want. The amateur radio licenses allow extremely high transmit power, anywhere from 200 watt to 1.5 kilowatt, depending on the level of the amateur radio license. And when you're seeing, these are a large number of frequencies, including nice ones, and high transmit powers. The reason that they're not being used by a bunch of, by many companies and other such uses is that legally they're only allowed for communication between amateur radio operators. There's no commercial use allowed, no music allowed, and the only case where you can communicate with non-hams is in emergency purposes. So the amateur radio system is mostly a number of people, including me as example, who use this system for experimenting, teaching radio frequency theory, and kind of community networks. And also it's used as a community service, like we've done walkie-talkies communications at the Manitoba Marathon. And it's emergency preparedness network, because it's well known that in times of emergencies, most cellular networks, which are not designed for, how to say it, overload, tend to fail. And in those cases, often amateur radio networks, because it's a number of more directly controlled systems, those tend to be extremely resilient. Most amateur radio usage is analog voice, think walkie-talkies, and pretty old-fashioned in that regard. Some new systems, such as D-Star or Fusion, are bringing in digital voice and allow more data communications. There are some frequencies or systems that use low-speed serial-type connections for general chatting or sending GPS coordinates for tracking networks and and various games like Fox Hunts, where people try to track down a vehicle or a device just to work on their radio usage abilities. There are a number of higher amateur radio frequencies, such as 2.3, 5.9 gigahertz, and even 24 gigahertz, which are not often used due to not much equipment being available. Some projects, including the VA4 WAN I'm involved with are work to take a commercial off-the-shelf Wi-Fi equipment at 2.4, 5.8 gigahertz and change them to work at 2.3 or 5.9 gigahertz to then do a citywide and later larger area amateur radio network that uses Ethernet protocols and tries to bring in more modern standards and more modern usage to some of these systems, which are pretty old-fashioned. There is some really interesting experimentation happening in amateur radio frequencies as well. In Winnipeg, VE4MA, Barry, he does some very impressive self-designed hardware. 24 gigahertz, as you can tell from the high frequency, doesn't go very far. Commercial antennas of those, you can get unlicensed commercial radios like the air fibers that go 3-4 miles, almost a gigabit speed. But 3-4 miles is kind of the reasonable max distance considering rain fade. This guy bounced a signal off the moon to Japan at that frequency. He got an old traveling wave tube, which is a really rare high-end type of amplifier that's often used for satellite communications and sells for 50 grand. He got it on eBay for cheap because it was broken, fixed it up, and then he attached that to a high-power satellite dish and designed his own hardware, with a modulation that is extremely low speed but survives extremely low signal levels. And he used that to bounce a signal off the moon and chat to a guy in Japan he knew. So a bit more expensive than picking up the phone and calling, but you can say that I think I don't know where he got like 8 or 10 foot satellite dish to actually do this. He works probably from his employer's old stock or something. But he managed, but that's a kind of experimentation which some of the hams are getting quite known for. And finally, we have the unlicensed bands. So these are the frequencies which most people in this audience use heavily with Wi-Fi routers, cordless phones, baby monitors, wireless security cameras, and the like. The most common ones are 900 megahertz from 902 to 928 specifically, 2.4 gigahertz, and various points between 5.2 and 5.8 gigahertz. The unlicensed spectrum is really wide, and anyone can use it without paying licensing fees. Now, the trade-off of that is that the transmit power is relatively low, the legally allowed transmit power, and there is no guarantee of interference protection. So if someone sets up unlicensed gear next door, if your neighbor gets one of those Graco baby monitors that transmits on the whole 900 megahertz band at the maximum transmit power, he'll probably wipe out your equipment, and there's nothing you can do. But these, because they don't need licensing, they can be immediately, quickly set up, and they're easy to work with for anyone who has their projects. The government still kept some type of control over this. You can only use type-approved equipment. That means that before someone sells equipment in Canada or the US that uses those unlicensed bands, they need to be evaluated by a laboratory to FCC, Federal Communications Commission, or Industry Canada standards. No one cares about Industry Canada standards, so we'll just mostly talk about FCC. And using the results from those labs, the FCC will approve the equipment for sale. These tests usually include that the equipment does not easily allow transmission above the standard, the maximum transmit power that should be allowed in licensed bands. And also, these tests verify that the equipment does not have spurious emissions. So to make sure that your 2.4 gigahertz Wi-Fi router, if it has an 800 megahertz CPU, it hasn't been designed without filters to save money, and then it starts transmitting at 800 megahertz and screwing up your cell phone at 850 megahertz. That kind of idea. So the US FCC has the Office of Engineering and Technology, which is responsible for that licensing, the verification of unlicensed equipment. And they have a very nice little database where you can go to the FCC ID search form and search by manufacturer and by model. If you have any unlicensed devices or Wi-Fi router and the like, and it has FCC ID ABC-1234, you punch it in there, and you'll get results that have lots of information that's only useful to nerds like me and possibly some of you. There's the test results of what type of frequencies they use, transmit powers. There are high resolution pictures of the inside of the radio, of the equipment, so you can tell what chipset they use, whether they use the little surge protector diodes on the Ethernet ports, and other fun stuff. And sometimes even, it's rare, but the manufacturers sometimes forget to send in the confidentiality form where they tell the FCC that they don't want these schematics or mode or like parts list to be made public. So sometimes you can go through the database and find occasional products where you actually get the complete schematics of the radio and parts list, which again, if you're an RF nerd, it's really fun to see how stuff has been designed. So about legality, this is what I think is legally correct. Again, I'm not a lawyer. You can receive any radio signals that you want, except in the US, you are not allowed to receive cellular bands or sell equipment which can receive cellular bands. Of course, sometimes manufacturers forget, or changing bits in memory kind of changes that fact. From any information that you do receive, whether with a scanner or SDR or other equipment, you're not allowed to reveal that information to anyone else or do anything based on that information. So you're not allowed to use it for profit or otherwise exploit it. You are not allowed to transmit without getting permission from the licensed frequency owner, such as getting a cell phone from those cellular companies. The only way for the average user to easily transmit signals is either getting the unlicensed frequency devices or be an amateur radio operator. And in both those last cases, most of the devices you buy, they are designed and if they went to the FCC OET process, they're supposed to prevent transmissions that are either out of band or at illegal transmit powers. There are some funny cases like that. For example, lots of Wi-Fi gear, one of the requirements for FCC certification for Wi-Fi gear is that they couldn't use common antenna connectors, such as the N connector. So a large amount of Wi-Fi gear was started being sold with RP SMA connectors, which is what the manufacturers called non-standard, so that people couldn't plug external higher gain antennas to the Wi-Fi products. And then everyone had RPSMA connectors, and now that is a standard. So the FCC's idea of like this, put non-standard connectors on your radio so that no Joe Schmo on the street can just plug in a high power antenna and go over and transmit at illegally high power levels, didn't work as planned. Also, you can get connector adapter kits. I got a nice one for about $200, which is a pack this big of every standard RF connector with little twist-on connectors, so you can connect anyone to anyone else. So you've got lots of options like that for connectivity. Here, as we go from the basics of RF to software-defined radios, we will go over the basic radio architecture so you get a bit of understanding of how these devices work. The basic radios I wanted to see are a consumer FM receiver, an unlicensed band cordless phone, and a Wi-Fi client. So if we go with the standard consumer FM radio, these are receive-only radios that can tune between 88 and 106 megahertz, approximately, depending on region, in 0.1 megahertz steps. Their data format is the radio station is constantly transmitting mono/stereo analog audio in a channel that's around 75 kilohertz wide. This system, like color TV, is intelligently designed for graceful degradation. You can consider it two modulations, stereo and mono, and the stereo is a higher bandwidth system because it's two audio signals. But the way it's designed is that if you don't have enough signal to get both, you'll still get mono. It's in the same way that if you don't have black and white and color TV signals are actually kind of two separate signals in one. But if you don't have enough signal to receive color TV, the black and white signal is actually stronger, so you'll still get the black and white signal. Unfortunately, that's more a property of analog signals, where you can receive some signal at lower quality, but you still have something usable, whereas in digital systems, it just cuts out because of the nature of digital systems. So next device is an unlicensed band cordless phone. So unlicensed band, we're talking about the 900 megahertz, 2.4 gigahertz, 5 gigahertz phone. Various phones use these different frequencies, or the 1.9 gigahertz DECT band, which is not exactly unlicensed, but it's can be legally used for cordless phones. There are some more advanced phones that use just one frequency and use a time division standard where they both use the same frequency, but the base station transmits, then the phone, then the base station, then the phone, etc. To keep things simple, I'll base myself off one of the simpler phones I have seen. They just saved money by just having two different radios and completely different frequencies, and they just transmit. That's it. All the time, as long as phone calls are active. So these cordless phones, all modern cordless phones use digital audio each way, and with channel sizes anywhere from maybe 1 to 8 megahertz, depending on what the manufacturer felt like doing, whether they wanted more range or interference survival. Over the air, it both includes the digital audio and commands such as go on a hook, go off hook, activate the ringer, the general phone commands. And for these, the general idea of when they transmit is once the actual phone connection is active, both ways are always transmitting. The last example I'll have is the Wi-Fi client, your laptop, your cell phone, something like that. There's a lot of unlicensed frequencies which are allowed for Wi-Fi. In North America, there's the 2.4 gigahertz band from 2402 to 2483 megahertz. That gives you 11 overlapping channels. But if you want to get the best performance, you need to set your equipment to be non-overlapping. And there's only 3 of those non-overlapping channels. Right, guys? There was a Hacker Jeopardy question on that, and people failed it often, and every time it annoyed me. Often with the same people, I think, doing the Hacker Jeopardy. There's also a few hundred megahertz of spectrum, a wide area, in the 5 gigahertz range. These standards use 20 megahertz wide channels. On the older protocols, the B and G, newer protocols such as N add wider channels for more speed, 40 megahertz and either 2.4 or 5 gigahertz. And the newest AC standard adds super wide channels, either 80 or 160 megahertz. And those 160 megahertz, not gigahertz, sorry. And those give a very high rate of data transfer, but also they use so much spectrum that it becomes a lot easier to interfere with neighbors or other equipment. And ignoring the rare ad hoc mode, the general architecture of a Wi-Fi network is that you have one access point, often your router, that broadcasts the beacon every 0.1 seconds saying, I'm here. And you have multiple clients, your laptop, cordless phone, etc., that connect to it. All Wi-Fi devices use a CSMA protocol. Very simple, and it's pretty much listen to the, check the error, if you want, for a short amount of time, making sure that no one else is transmitting. And then if no one else is, you assume it's okay for you to transmit, so you do so. And if someone else and if another device happened to be transmitting at the same time, then there's data loss, and the receiver does not send an acknowledgement that the communication was successful. So the transmitter redoes the transmission. That gives us some really low efficiency for Wi-Fi standards. For example, N Wi-Fi equipment are often set on the box to be 300 megabits, assuming that we're talking full channel width, 40 megahertz, and 2 spatial streams, so 2 antennas, each sending a different version of the data. But the actual efficiency, if you look in, for example, the small net builder router performance charts and extremely in-depth overview of routers and their speeds, the top of those charts is only 155 megabit, so that's like 50% efficiency. Not really good. There are some TDMA implementations where people took standard Wi-Fi chips, most of which are actually an ARM processor, and reprogrammed them to have a TDMA standard where there's always one side transmitting. The access point tells the clients when they can transmit, and it's really much more controlled, and those get much higher efficiency. There are some that do 220 or 250 megabit out of the theoretical unattainable maximum of 300 megabit. Those are not Wi-Fi compatible, they are proprietary systems, but it's an example of how changing the protocol can be a lot more efficient. The Wi-Fi standards have many speed options. Depending on the signal to noise ratio, they'll switch modulations between really low speed ones and higher speed ones, depending on how much signal there is between the client and access point and how much interference there is that is affecting their transmissions. And the multiple spatial streams is something that you only see in more advanced systems, where you can have routers with 2, 3, 4 antennas, and they both transmit data at the same frequency. But because the data is kind of offset from each other, they don't exactly interfere with each other. So you can still get kind of double the speed because there's 2 antennas without them interfering with each other. That gets into more advanced theory, but it is one of the interesting parts of the protocol. So here I'm going to draw out the circuits of these various radios so you get an idea of how they work. For now, we'll ignore components like filters, which are well, we'll go over that later. Up-down converters. It can be difficult to make, for example, Wi-Fi chip that runs at the full 5.8 gigahertz to decode. Like you can't even buy Intel CPUs at 5.8 gigahertz. So a lot of circuitry actually down converts. They get the signal in at 5 gigahertz, then they use a mixer to take out that same signal at 1 gigahertz, and then they do their work on it. And yeah. So here's the circuit example for the FM radio. You have an antenna. It goes, first thing it hits is a receive amplifier to get the most reception you get, to get the best reception possible. You hit the amplifier first. Then you go into a tuner to tune to the exact frequency you want. It goes to an analog digital converter, which takes this analog signal and digitizes it so you can keep the best quality. It goes to an audio processor, which adds bass, treble, whatever effects you want. Some radios even have artist information encoded in like a sub-frequency of it. And then it goes to your audio output or your speakers. Here we have the circuit for the unlicensed band cordless phone using 2 different frequencies for reasons of simplicity. So say we're talking about the handset. If it's receiving from the base at 2.4 gigahertz, that goes to a receive amplifier, a tuner, because most cordless phones have multiple channels in case of neighbor or other interference, an analog digital converter to get these radio signals into something the circuitry can understand, a demodulator, which actually does the decoding of the complex signal into something like straight serial data, and then a processor. And the processor which runs the user interface, does the audio, etc. And for the handset to communicate back to the base station, it goes through the opposite process. Takes the serial data, modulates it into a more complex radio signal, does the digital to analog conversion to actually turn it into an AC signal, and then tunes it to the right frequency, and then amplifies it and transmits it out on this model of cordless phone on a different frequency band, just to save money. For Wi-Fi clients, that starts getting into much more advanced designs. You have one antenna, or more than one antenna. This example uses one. It goes to a receive or transmit switch, depending on the logic of what time it's for. There's a receive or transmit chain that does all the signal decoding or encoding steps. There's multiple levels of modulation at which the chip, the Wi-Fi signal, can transmit or receive. And inside the Wi-Fi processor, there's lots of advanced logic. The CSMA, so it decides when there's no other transmissions, when it can transmit. The decisions on at what speed to transmit, at what modulation. The reception acknowledgements, so when it receives data, it tells the other side it got it, so the other side knows it doesn't need to retransmit data or shift to a lower rate. And there's general network maintenance. For access points, always sending the beacons saying I'm here. For clients, always, if they're not connected to an access point, scanning for them and doing the connection process. And there's, of course, all the logic other than that to actually take the Ethernet data, your data packets, and send and receive them over the wireless network. So when you start looking at all these circuits, you start noticing the huge similarity between them. If you think them over, lots of the tasks, or I should say, the antenna, amplifier, analog digital converter, or digital to analog converter, and tuner, that all needs to be hardware due to the system requirements. But everything else, like all that complex stuff in the Wi-Fi system, that can all be done in software. And because the amplifier, the analog digital or digital to analog converters, and the tuners, those are devices that are easier to manufacture pretty wideband. Due to that, it gives you an opportunity to create a system that can be extremely that can emulate or be extremely compatible across a variety of wireless frequencies and modulations. Yeah. So that gets us to software design radio. Commercial units have been sold for thousands, tens of thousands of dollars for 30 years. But recently we started seeing consumer or prosumer units in the last 10 years. The Ettus USRP is one of the most known ones. So these devices are really wideband. They can receive a wide variety of frequencies. And except for the very basic one, they can also transmit a very wide variety of frequencies. They have analog to digital or digital to analog converters that can get a lot of detail. So you have, so they can understand a variety of signals. And these have a very fast interface to your PC, so your PC can do the actual complex work of signal processing, encoding, decoding. Some have a standalone processor for simple processing or decoding, but that doesn't, the standalone ones don't get you much. So here we'll review a few software-defined radios, all prices in Canadian dollars. Ettus, one of the biggest manufacturers, has 4 families. The commercial range, which starts $6,000 and plus. The networked range, which uses gigabit Ethernet and is in the $2,000 range. The bus series, which is around $1,000 something and is in USB 2 or USB 3. And they have embedded versions which have their own processor, which can handle some simple tasks. This unit is the USRP N200 or 210. There's 2 versions. It costs $2,300 for the smaller version with FPGA, a signal processor that can do about capture of a 25 megahertz wide channel, or $2,700 for a larger signal processor that can capture a channel 50 megahertz wide. The digital to analog converters can do even wider if you know how to program the FPGA to do that. It has a gigabit Ethernet interface to the PC, and it has independent transmit and receive channels, so you can do both at once. The DACs or ADCs are 12 or 14-bit resolution. It has an external clock input to synchronize if you want to get the exact frequency. Most of these don't have excellent clocks. You need an actual GPS-controlled frequency generator if you really want to hit a frequency bang on. So those have those external inputs. This does not actually do the tuning. You buy daughter boards that plug in and that handle certain frequency ranges. So you can buy basic one, which is from 1 to 250 megahertz, either receive or transmit separate boards. They're $120 each. Or more advanced board for $700 that ranges from 400 to 4400 megahertz in transmit or receive. Lots of other options. Next example is the bladeRF that just came out. It's $550 for the basic unit with a smaller FPGA, $800 for the one with a more advanced FPGA. These use the USB 3 connection to a PC. They can send or receive from 300 to 3.8, 300 megahertz to 3.8 gigahertz. And they have independent transmit and receive channels, so they can do both at once. Between the FPGA and the analog to digital converters, they can send or receive channels up to 28 megahertz wide at a resolution of 12 bits. They do have an external clock input for exact bang-on frequencies. And you can buy a transverter to go down to very low frequencies for $270. Next example is the HackRF One. It is connected by the USB 2 protocol. It retails $400. It ranges from 1 megahertz to 6 gigahertz. It's half duplex, so you can only transmit or receive at a certain time. You can't do both at once. The capture bandwidth is only 10 megahertz, so a bit more limited what signals you can capture. The sampler is 8-bit, so you get a bit less detail that way. It still has an external clock input, and it's fully open source, so you can even build your own, to my knowledge. There's a very nice add-on called the Portapack, which you can carry with you and to do a handheld unit. Another example is the Realtek SDRs. I'll be done in a few minutes. These are sold as very cheap HDTV receivers. The idea is hardware decoding of HDTV signals are advanced modulation. Hardware decoding is difficult. So they designed this as a very simple SDR, and then they let the software do all the hard stuff. It receives a very wide range of 24 to 1700 megahertz, but the resolution is lower at 8-bit, and it only does up to 2.5 megahertz bandwidth, so not a lot of signal options. And it's receive only, but for $15, you can't complain. Bandwidth requirements. So depending on how wide signal you need to receive, the bandwidth from the SDR to the PC can get quite high. For example, if you want to decode a Wi-Fi signal of 20 megahertz wide, the Nyquist theorem says that you need to capture that at 40 mega samples per second. If you want to get lots of resolution, say 12 bits, that ends up being 480 megabits per second of data that you are capturing. And only USB 2 can't handle that, only the other interfaces. Because these boards has FPGAs, you can use that. The FPGAs can do compression before the data goes on your PC, or even you can do some decoding on the FPGAs. Two other models, FunCube, it's more for amateur radio use. Yeah, wide frequency range, low price, but the channel width is only 0.1 megahertz, so it's just for like low analog voice or low speed data. And the PerVices hardware, which is really nice in terms of channel bandwidth. You can capture up to 200 megahertz wide channels, just huge channels, but they start at $2,500. Pros and cons of SDRs. Pros, they're wideband. You can receive any frequencies, any protocols, or wide number of frequencies. They open the field of RF. Cons, the cost. If your large channels or higher fidelity, it'll be a few grand. Yeah, sorry, I'll be done soon. Yeah. The size compared to like standalone hardware and all the processing required to work on those signals. And a big one is lack of filters. If you're receiving signals, they're very vulnerable to local interference because they don't have filters that radios for certain frequencies have. Similarly, if you're transmitting signals, you have to be legally careful because it is always possible they transmit out-of-band signals and you're interfering with something else. Wideband antennas, those are more difficult to do in antenna design. If you're optimizing for bandwidth, you lose a lot of other antenna, focuses, like low cost or low size or even high gain. So most wideband antennas are either very expensive, very low gain, or have other drawbacks. Examples of software-defined radio use. Tools, you can do a spectrum analyzer or oscilloscope, popular electronics testing or analysis components. Those can be a few $100s to a few thousands. You can do a basic one with an SDR. The big problem is that they're not calibrated, so you're not guaranteed to be hitting the exact frequency or signal level that you want. GQRX is an example of free software that uses an SDR you own to receive and even decode some various signals. OpenBTS is you create your own cell network by it emulates a GSM cell phone base station using SDRs. It has been used as Burning Man and even some small, even countries, I think, for people building their own cell networks. Because if you get a license to use these cell phone frequencies, like 850 megahertz, you can legally use these as a cell phone base station. But in places like North America, I mean, another option you can is there's lots of European cell phones or standard cell phones that can be set in a Europe mode, and they'll look for cell phone signals in the 900 megahertz band, which is unlicensed here. So you can set a base station in that 900 megahertz band and find cell phones that'll connect to it and kind of run your own mini cell phone networks. These do require high power amplifiers to get more range. And because 900 megahertz is unlicensed, there's lots of local interference. So it could be a baby monitor next door will kill your cell phone network. GNUradio is software where you can design radio architectures and that'll connect to SDRs to run as receivers or transmitters. So a lot of those designs I showed you earlier, you can recreate them in GNUradio to create a receiver or transmitter with modulation, with lots of other signal processing. And 2 minutes. Security implications. Radio systems used to be considered kind of a black box. There's lots of links, such as SCADA links between, say, factories or plants that were set up as serial links without encryption, without authentication, for a few reasons. People thought no one uses these radios, or our company uses it internally so no one else has access to it, or no one can make a radio powerful enough to decode signals. So a lot of these assumptions that allowed radio links or even full radio systems to be set up pretty much without security no longer exist now that SDRs are here. There was DEF CON 23 talk, which I really recommend you look at. Kobe Moore founded a satellite data system that used for tracking asset, did not use data encryption or authentication. It just broadcasts in the clear. So pretty much and this has been used for 20 years. And data is just broadcast. Anyone can listen. Anyone with with the correct radio SDR, anyone can send or receive these signals. And a lot of security processes were put in, assuming that this data was secure and controlled and authenticated, which it's not. Some radios used to be deployed with FHSS security, where the radios themselves hop different frequencies. The data wasn't encrypted, but the companies said because the hopping pattern is so complex, no one can listen or transmit. But with an SDR, you can actually capture the entire band. You can capture all the possible frequencies and then decode them all at once. So the assumption that FHSS radios were secure by their hopping doesn't exist when any SDR can capture all the frequencies at once and decode them. And another example seen at DEF CON 23, GPS system spoofing. A lot of processes were put in assuming GPS was correct and authenticated data, but it turns out that you can spoof with an SDR. You can fake locations, you can fake times, and all of that means that processes which assume GPS was secure or even true are not that secure. So SDRs, they open the black box of radio. Thanks you all for listening. Thanks to BSides Winnipeg and Skullspace for allowing this talk. I am considering doing an occasional SDR group meetup at Skullspace or maybe even some kind of mini conference. So if you're interested, please email me at that email address or let me know. I bought a few SDRs for my own project, a USRP N210, a bladeRF, and a HackRF, and I have lots of antennas and junk. So if you're interested in playing with some, let me know. And last recommendation, get into amateur radio. There's work meetings every month. There's basic license class, which I'm one of the professors. And that allows you to bring up RF knowledge and really start understanding these systems. And if you're interested in it, that's the best way to really start getting involved in radio work. So thank you all for your time.